Let us continue our discussion of duality. We will try to wrap it up today or maybe in the next lecture. So, we were talking about the fact that the dual function this is a concave function in lambda, sorry lambda mu, jointly in lambda mu it is concave. So, we need to now look into the dual properties of this function. When if it is concave, then its negative is convex, then can I find a subdifferential and all those things, and when it is differentiable, that is also a question. So, we will start with one example from the text by Andreasen, F. Grafov and Michael Patrickson. This text is called an introduction to continuous optimization. This is available in India, and in fact it is an Indian print that I am trying to show you. An introduction to continuous optimization. It is published by Overseas Press in India, and it is by Michael Andreasen, F. Grafov and Michael Patrickson. Michael Patrickson is a very renowned optimization researcher, and let us tell you something before I actually give that example from that book, that showing that okay, there can be a situation where theta lambda is actually differentiable, not just non differentiable. The interesting part that I want to tell you is that okay, if I make the problem slightly more complex, we add an additional constraint. So, these constraints are hard constraints like bounds on the variables. So, in this particular, if this is the situation, then my Lagrangian only consists of the functional constant, and this is a non-functional constant as such as it is represented. Of course, if you have xi between, say written all the xi's are between -1 and +1, then of course you can write done them as inequality constant, but you basically would increase your number of constants. So, in order, and you would make the Lagrangian look quite complex. So, in order not to do that, one can put it in this form, and then you can again write the Lagrangian as the same Lagrangian, but in this particular case, when you write the dual function, your infimum of x over x is no longer over Rn, but would be restricted to this particular set x. Okay. Now, let me provide this example. So, the problem is to minimize. So, this is a convex function x1 square plus x2 square. So, x1 and x2 are in R. So, it is a problem in R2, basically I should write x is in R2. So, you are minimizing over R2 subject to a linear constraint which is and x1 is greater than equal to 0 and x2 is greater than equal to 0. Now, these constraints are hard constraints, means even if you in real application, means when you are actually applying the algorithm, if there is even a slight violation of this might not be of so big harm to the problem, but any violation of this would actually change the problem. This cannot be violated. This is called a soft constant and this is called a hard constant. I told you quite often. So, this I can write minimum of I can write this as So, there is one only inequality constant and I can write x, the x variable which is x1, x2, write it like this, is in R2 plus, that is in the non-negative orthant. So, that is essentially the problem. Sorry, I made a mistake in writing this. I should have written it like this instead of putting it like that. I can write it as 4 minus x1 minus x2. Now, if I form the Lagrangian function, I will only club these two in the Lagrangian, I will not keep in that in the Lagrangian. So, here I have one constant, so Lx lambda would be now theta lambda, maybe no sorry, not mu, sorry, that is a mistake, should be lambda. Now 4 lambda is a constant because I am fixing a lambda and then minimizing. So, my theta lambda in this particular case is to minimize over x element of R2 plus. So, here I am restricted of this Lagrangian function. Now, observe that here I have made this restriction quite similar to the one here. Now, once that is done, here you see lambda is fixed. So, 4 lambda is something which I can take out. So, if I want to now find theta lambda, basically I am calling for the minimization of, let me now write the thing in a proper way. So, 4 lambda is something I can need not bother, and you can take it outside the minimization, plus so you see these variables have got decoupled from each other. So, when you want to minimize such a decoupled function, that is, please remember this very simple formula which you can prove. So, you want to minimize this over x y, and this is simply nothing but inf of f x over x plus inf of g y over y. So, now if you want to do this and this, these are decoupled. So, this is acting like f x and this by like some g y. So, 4 lambda can be taken out. So, I can write this as minimum over x 1 greater than equal to 0, x 1 square minus lambda x 1 plus minimum, infimum actually, but you can actually figure out the minimum of this, x 2 square minus lambda x 2. Now, let me tell you that the minimum of this is obviously depending on lambda, and that is given by lambda by 2, and this one is as same as that. So, that is looks just the variables are different, instead of x 1 x 2 it is same as lambda by 2, and theta lambda you can calculate out to be this. So, you see this is a differentiable function. Now, do not tell me how to calculate, ask me how to calculate the minimum of this one, because this is a real variable thing, you can just figure out yourself. Now, the question would be, if it is not differentiable, if it is concave, so its negative is convex, can you find the subdifferential? Can you compute the subdifferential? This is a very important thing that one has to know, that okay, suppose I now take the problem this one, but I cancel the equality constant and cancel this one, I just keep inequality constant. In that case, my Lagrangian would look like it will look like this, it will absolutely be of that form. Now, theta lambda is inf of f x plus now depending on the lambda the solution set will change. Of course, I am just infimum is over whole x, all the x. Now, the question is, I really do not know whether a minimizer of this exists or not. If a minimizer of this does not exist, you cannot tell, you can compute the subdifferential, but it would be too complicated. It will be extremely complicated. Now, if I do not know about the, if I know about the minimum set, that is okay, given a lambda, I have an x hat which is in the solution set, then I can tell something about the subdifferential set at a given lambda. So, let me just take this part and describe you this fact. Now, let me look into this simple fact. Now, say S lambda is the argmean set that is any, this consists of all x such that, all x hat such that theta lambda is equal to f of x hat plus summation lambda I g I x hat. That is what it means. There is a set of minimizers of this problem. That is all. Now, suppose our S lambda is non-empty, S lambda, say take S lambda bar is not phi, and let us take x bar is element of S lambda bar. So, let me just have this information. Once I have this information, what can I do? Okay. Let me take any other lambda other than lambda bar, and then let me now try to deduce something. So, take some lambda, need not be not lambda bar, take theta lambda. Now, theta lambda is that inf of f x Now, this one is less than, obviously, because x bar for particular choice x bar this infimum is, sorry infimum is less than or equal to this. So, what I now do is I add and subtract from each of these lambda I bar g I x bar. So, this will give me This is simple algebraic manipulation. Now, this simple algebraic manipulation will immediately show you what you actually want. So, this I can combine this to write this as theta lambda bar, because x bar is element of s lambda bar. So, theta lambda bar is exactly f of x bar plus lambda I bar g I x bar. Now, these two combines to give me theta lambda bar, and here I can write it more in a compact fashion and writing this as lambda minus lambda bar, where gx is the vector g1 g1 g2 dot 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 gmx. Now, what does this show me? This show me that if I take a minus sign, because then I will have minus theta lambda bar, because this will be minus, this will be greater, my minus of minus theta lambda bar plus theta lambda bar, basically I will take it to the other side. This will become minus here and then go to the other side, is greater than equal to minus g of x bar lambda minus lambda bar. So, what does it show? This immediately shows me that minus of g x bar is a subset of the subdifferential of theta at lambda bar. Okay, this is what you have. This is this. Now, say for any x bar which is here, this is in the subdifferential. So, I can write finally, because this is a convex compact set, finally I can write that the convex hull of minus gx bar is where x bar belongs to S lambda bar is a subset of the subdifferential of minus theta at lambda bar. But now I will give you as a homework for those who have taken a look at the separation theorems from the books, just knowing the statement will do. So, if you know about the separation theorems, this is a homework. Now, apply separation theorem to show that del of minus theta lambda bar is convex hull of minus gx such that gx bar such that x bar element of S of lambda bar. This actually there is an equality. So, this is a very fundamental formula. Now, if I say that instead of Rn here I have capital X, and if that X is compact, then such a thing is anyway guaranteed. So, that S lambda bar is non-empty. So, here the formula that you see is computed only under the assumption that this is non-empty, which is not always easy to guarantee, but in many cases yes. Now, for example, here whatever be your lambda, these are my solutions. So, theta lambda is always this, right. I know the set of x's solutions. Now, what I am trying to tell you is the following. We have discussed about the differentiability property of the dual function. We have also spoken earlier about something called weak duality, which says that the minimum value of the primal problem is always bigger than the maximum value of the dual problem. So, the dual problem provides a lower bound to the optimal value of the upper to the primal problem. Now, the question does not lie like this, the question is the following: when are these two equal, that is when strong duality will hold, and that is exactly what we are going to discuss at this moment. So, we will now talk about strong duality as we had just spoken. Strong duality, that is the equality of the primal value and the dual primal optimal value and the dual optimal value. So, what does strong duality tell us, and how do we prove strong duality? Now, here let me tell you that strong duality is always guaranteed for a linear programming problem. Strong duality is not always guaranteed for a convex programming problem, and for a non-convex problem it is never guaranteed. Under some conditions for a convex problem, for a very simple conditions, you can always be sure that the strong duality holds. So, the problem that we had spoken of is the projection problem, where we showed that geometrically strong duality holds, is a case where all the conditions are satisfied. Now, let me tell you following thing. Suppose I have a differentiable convex optimization problem. Just with inequality constants. So, this is convex. So, when strong duality comes, we are actually in the fold of convex programming. Assume that these functions are also differentiable. So, assume that these two are this m plus 1 differentiable convex function. Now, once I know that, let me assume an important condition, a constant qualification called the Slatter condition, of which you already know. That is, there exists x hat such that now, once you have that, and if x bar is a local minimum, sorry, not a local minimum, very sorry, it is a global minimum, convexity there is no local minimality. If x bar is a global mean, of this problem, which I can call for the time being CP to refer convex programming, then so if this holds, if x bar global, then on if Slatter holds, Slatter condition holds, we know that the Karush-Kuhn-Tucker conditions hold, the KKT conditions hold. That is, that is there exists lambda bar element of Rm plus such that f of x bar plus summation lambda I bar, sorry, gradient of g I x bar, this is 0, and number 2 comes the complementary slackness condition, which we have mentioned many times, is 0. Now, look at the first equation. What does the first equation say? The first equation says that if I fix my lambda bar, then this is 0, and the derivative been taken over x, the partial derivative is only over x, which means, but the Lagrangian function f x plus summation lambda I g I x bar is a convex function now for a fixed lambda positive, non-negative. So, obviously, this lambda is non-negative. So, and the convex function x bar is a critical point of that convex function, which means L x bar lambda bar. So, this is an unconstant problem, is the minimum of L x lambda for all x element of Rn, and this immediately tells me L x bar lambda bar, sorry. So, you see we have recovered one side of the saddle point conditions from the Karush-Kuhn-Tucker conditions. So, it is a reverse way of looking at the thing. Now, if you look at this, if I break it up knowing that lambda I bar g I x bar is 0, so I will simply have here is f of x bar, which is now is the minimum value of the problem of the primal problem, is less than L x lambda bar for all x in Rn. Now, this is a fixed quantity here, for whatever x you choose this would be bigger. So, this would imply that f of x bar is less than equal to infimum of L x bar, and this is nothing but theta lambda bar. So, what we have obtained from there is f x bar is less than equal to theta lambda bar. But if I go back and look at my weak duality, then I would have theta lambda bar to be less than f x bar, because x bar is feasible to the primal and lambda bar is feasible to the dual. Lambda bar just has to be greater than equal to 0, that is the dual feasibility condition. Dual feasible set is always non-empty in this particular case of Lagrangian duality, which means that f of x bar is equal to theta of lambda bar. Now, you take any other lambda which is feasible to the dual, that is lambda bigger than 0, then by weak duality again you will have this, which means lambda bar maximizes theta. Lambda bar maximizes theta. Okay. So, which now means, so lambda bar maximizes theta, and at the same time we also have f x bar is theta lambda bar. You also have f x bar is theta lambda bar. So, what does it say? It says the maximum value of the dual problem is same as the minimum is equal to the minimum value of the primal problem, and this is exactly what is strong duality. This is exactly what is strong duality. Now, there is the interesting thing which I will not analyze here, because it will be beyond the scope of this class, beyond the scope of this set of very basic lectures, is that if I do not know about what is the x bar which minimizes the problem, I only know that this problem has a lower bound, then I can still show that the dual maximum is achieved at some lambda bar, and the lower infimum of the primal problem is same as the maximum of the dual problem, but that we will not discuss here at all. What I will tell you is that this show you now is that this Slatter condition is a very important condition. If I take off the Slatter condition, if I have a convex programming problem and the Slatter condition fails, this strong duality will fail to hold, that is f x bar would be strictly bigger than theta lambda bar, and that is what we are going to now discuss through what is called the Duffins duality gap. It is very famous example due to Richard Duffin. Now, what I will do is the following. I will write down this very famous problem. The problem is to minimize subject to the first thing that you have to observe, that when I write root over x1 square plus x2 square is less than equal to x1, it simply means x1 square plus x2 square is less than equal to x1 square, which means x2 is equal to 0. So, if I put x2 equal to 0 and take any x1, then my feasible set, my feasibility is guaranteed. So, the feasible set C in this particular case is a set of all x1 0 Of course, if I have to maintain this one, because here if I take a negative number, say I take minus 2, so minus 2 square plus 0 is 4, root over 4 is equal to minus 2. So, minus 2 cannot come here. So, what has to come is r plus x1 has to be greater than equal to 0. So, I cannot take a number by the very expression of this inequality. I cannot take x1 to be non negative. So, that is my feasible set. Okay, now let me write down the Lagrangian function, which is now look at the whole thing very carefully. Now, if x2 is 0, then the primal optimal value, there is a primal problem, primal optimal value is equal to 1. Now, let us look at the dual optimal value. How do I compute the dual optimal value? Now, my theta lambda is equal to is same as Now, let me look at this whole thing. Now, what I will do, let me fix up a value of x2 and now vary x1. So, once I fixed a value of x2, this is a function of x1. So, on this line for a fixed x2 on this line, I need to find what is my minimum of this function and then I will vary the x2. So, basically I am sweeping this horizontally and then sweeping this vertically, means I am covering all of R2. Now, look at this, when x2 is fixed, as I increase my value of x1, as I make x1 go to infinity, make it bigger and bigger and bigger and bigger and bigger, this part goes down to, the difference between this and this continuously decreases, that is x2 gets fixed and x1 becomes so large that it dominates and x1, so value of this is almost same as this. So, the difference between root over x1 plus x2 square and x1, that continuously diminishes and hence now, so on this line, the minimum value of this problem on this particular line for this fixed x2, say this is my x2, this value is e to the power x2. Now, now I try to vary x2 over this line and see what is the minimum of. So, basically what I am doing, minimizing over x1 and then minimizing over x2. Now, if I vary x2 along this line, so as x2 goes towards minus infinity, e to the power x2 goes towards 0. So, the theta lambda value is actually 0. So, max of theta lambda when lambda is greater than or equal to 0 is also 0. So, you see there is a duality gap, the optimal value of the dual is 0, optimal value of the primal is 1. And so, there is a non-zero duality gap of 1. So, this is a very famous example and I think your optimization education or even in the fundamentals will not be complete unless you really understand this example, and it came out in a very famous journal, Math Programming. And see, again I would like you to notice how I have done it. I have first fixed up a x2 and minimized this function over x1. So, I have covered this part. So, what I know the minimum value of this function over this line. So, for all such lines whereas I fix x2 from here I go down, I know what is the minimum value. So, the minimum value of the function over the whole x1 x2 plane is what I get as I make x2 go to infinity minus infinity, once I know the minimum value over this line when x2 is fixed, and that is e to the power x2. So, and that is how we obtain our problem. So, here we have almost done a lot about duality. We have done various properties of duality. I will give you a small example when I begin tomorrow's lecture as to how I can make this duality useful. First of all, you should notice that how can I actually apply this duality, this idea to real problems. Of course, I will give you some homework, not to really do, but go and try to find in the internet, find the text that show that if you have a linear programming problem, then to get strong duality you do not require any constant qualification, no Slatter condition, nothing, and you will get the same, you will always get strong duality. Now, just go and find out from the internet, but I will still want you to tell me what is the proof. The proof again would be based on the approach that I have taken through Kuntakar conditions. So, maybe we will do tomorrow a bit of duality for half of the class, and then we will show how can we use again the idea of the projected, not gradient but projected subgradient method to actually make the dual problem computable. Actually, we can do some computation with the dual problem. That is what I am going to demonstrate in the next class. So, I think this is almost towards the end of the course, and we will have, after tomorrow's class we will have 3-4 more lectures. So, of the 3 lectures, one will be trying to describe to you what is how to apply Newton's method to constant problem, and probably if we have time we will talk about the sequential quadratic problem, and at the end we will give you a brief idea about the new approaches, not a new approach, a old approach now given in a new box, because now it has revealed a lot more properties called the direct search method, because we now have convergence analysis for that. See, when you do optimization algorithms, it is very important that you just do not bother about writing an algorithm and say whatever I have got is fine. You have to show that whatever you have got is fine, and you have to do it mathematically. You have to show under what conditions that the sequence that your algorithm would generate would either go to a critical point or hit the actual solution. So, these are very important aspects that you want to do when you want to design optimization algorithms. So, thank you for listening to me, and we will continue our discussion of duality and bring in some subgradient time methods, the use of subgradients to solve non-differentiable convex function convex problems in tomorrow's class. But it is very important for you to realize that non-differentiability is a very important thing in optimization, because when you want to use this dual problem for a convex problem or any non-convex problem also, your dual function is always a non-differentiable, usually a non-differentiable convex function. So, it is very important to know that non-differentiability is something which you cannot get away with in optimization, though when you have started learning basic maxima minima, you had really bothered only about differentiable functions. So, optimization is really not about differentiability, optimization is essentially about non-differentiability, about non-smoothness, and that is something you have to realize if you want to have your foundations quite strong in this area. Thank you very much.